howdy, howdy. Alright, today let's look at arrays. Fun with arrays. Oh, I say that as we get started. Okay. So let's look at an array and see. So I like to use let's do uint64t pointer. My array uint64t times 100. And this is in standard int. I think so. Oh, I also need standard lib for malloc. There we go. So if we do dump let's see, what's this called? This is called arrays. And we do main. Okay. So allocating, it's one thing. The access is where it's more interesting, right? So this will figure out how big is this. So these are sort of known, right? Your size of your uint64t, that's a known value. So that should be 8 times 8 is 60. 8 times 16 times 4 gives us 64 bits. So it should be that times 100 in number of bytes. But when you try and access anything in there, so if you do my array bracket 1 is equal to negative 128. We'll do a make and then run that. So we can see here, so malloc is called here. The result is stored in RBP -8. We're then moving that value into RAX. So that's our address of the array. And then we are adding to that 8. And then we're moving our nice negative 128 into that location, right? So it's doing that. It's a little more clear when you put it in a loop. So for example, for int I is equal to 0, I is less than 10, I plus plus plus. So it's going to use I as our index. And then if we, instead of using 1, use I, so now it's going to use that as our index. So let's see, where does I get set? I is at 0, so I'm going to guess, okay, I is in RBP -10. I think that's right. Move RBP -10 into EAX. Here we're clearing the direction flag, I believe. We're then taking, it's interesting that it used EAX. but we're taking RIX times 8. So that is our offset. Okay, that's why it's an offset. So it's going to use that as the maximum amount. Yeah. Oh, I guess I is declared as an int. So if I declared I as a long, or a uint 64t, then it will probably RBP minus 10. Yep, REX. Yeah, so that's why it used this small, because I was just being lazy, using an int there. So, all right, so every time it's going to do an increment of that pointer, it's going to use whatever the size of that thing is, and that's how we do our single dimensional pointers. Now with that, that's pretty easy when you have something like this, but let's say we go grab a structure. So let's make a structure. I'll go grab some code here. Let's look. All right. Just pick a random structure. Okay. So now if I were to, so this is just an int and a character. I mean, let's just do a couple of other things. So z. Oh gosh, it's been a while since. I am used to Java. I have to say struct. Oh goodness. So this is going to be on the stack, or on the stack. Z dot my letter equals A. All right, let's build that. Did that build? Yeah, looks like it did. Okay. Okay, so we can see our cafe here. Right, and so it calculates the offsets. So it looks like it's using it on the stack. My num is first. So it should be allocated first. So it's at RBP minus 8. That takes up 4 bytes. So that's why this is at 4. But when you start allocating them, then it'll calculate those offsets. So size of my structure times, say, 10. I get my multiplication in there. Oh, did I need to put this structure pointer? It's been a while. Struct. I'm guessing. And then I got too many. Yep, too many. Okay. So then when you go and try and do something with this, you're going to have to say ZZ bracket 0 dot my letter equals quote B. Actually, this, yeah. My num is equal to feed. All right, so we can see So again, it's at the beginning. So the pointer is stored at RBP minus 10, and we should be able to see that in malloc. Malloc is called through the PLT. Result is in RAX. RAX is moved into RBP minus 10. So that's where our ZZ pointer is. So that's in RBP minus 10. Of course, then it has to reload it into RAX. And then we add 4 to that pointer to store our B, which is the number 62, because the way that the C structures have to work in order for things to be compatible is that you have to do them in order, and you have to allocate the correct number of bytes for each thing, doing some rounding. So for example, if I did a uint 64t my 64 as part of our structure, and we did ZZ bracket 0 dot my 64 is equal to 0x feed face. Again, picking some value will sure to be seen in here, so we can sort of back our way into it. So move ECX feed face. We're then moving that into RAX minus or plus 8, right? So this is at offset 0. That takes up 4 bytes, so this can go to offset 4. But even though this only takes up 1 byte, it actually has to give it space unless you do an option to compact it. So that's why it goes in at offset 8, right? So this, we waste spaces 5, 6, 7 and move to 8 as our next one. I know I can't spell. So we can see how those manifest themselves inside of there. Which, you know, it's pretty simple here in the land of C, but it actually becomes a little more interesting when you jump to C++, because then C++ stores pointers to functions using the same sort of method. So we probably won't cover that today, but that is definitely something that it will do. That's how they do that internally. That's how. So, you know, it's the pointers and the structures, right? So that just sort of depends. Now, if we were to go to structure 1, then we would see the actual size of what it thought this was. So ZZ bracket 1 dot my 64 is equal to something like that. So it will, let's see. So we'll load our pointers in RBP minus 18. So we move that into RAX. And so then it adds 16 to it. So it says that this structure is of size 16 when you do a pointer increment. So every single time it's going to be size 16, which makes sense, right? So we had 0, 4. So it starts at offset 8 and goes through bits 16. So that's why that is 16. If we added another char here, then when we go and look at that, again, it's got to take up additional bytes. So it actually did 18 for that instead of 16 that we had before, right? Let's see. I guess it depends on how it wants to round up. It was 18. Char ZZ. Let's do it. I guess it rounded up already. Oh, is this going up to... It started at 8. Oh, was I looking in the wrong spot? Let's see. Oh, is it? No. Yeah, it's at 28. So I guess if I added, let's change this to a... This is a funny thing about compilers. They're going to make up, they're going to do their own thing. Well, we should see the call to malloc. So there's our call to malloc. It's in RBP minus 28. Add RAX 18. So that's our offset into there. Should allocate more. Maybe it's below the threshold where it now decides to do new ones. So sometimes that depends on those C compilers. I think if I did this as an array, size 100, or is it not compiling? Oh, I did the wrong one. Oh, no wonder. I'm an idiot. I was not recompiling it. Okay, comment that out. Comment that out. All right. So this is the one I want. Make and dump. Okay, it's 10. Now I add 1 to it, and now I get 18. Yeah. So it added 8 bytes. Just to get that one. Like I get as much with this. All right, still get 18. I mean, one of that partially proves that you should just make sure you're ordering your structs the right way. Like generally what I would say is either you put all of the bytes at the beginning or at the end, unless you're doing a spec that is something that is open to anybody, and then you might have reserved ones in there. So I know Microsoft does that in their specs of their structures. If you go look at the PE structure, let's see. If we can pull up PE structure. Let's pull this out. So they end up having some things where it's like reserved, like this you know, they're not using every single bit that they've defined in a lot of these things. They are reserving some for, you know, what they, let's see. Reserved must be 0. Right, so they define that they're going to reserve things and not keep them around. Like, they'll keep it around, and it will use extra bits, but when you're looking at what the loader is going to do, right, it wants to load things on these even byte boundaries because it can load them faster, because it's not having to possibly go across different pages or different bytes in memory, so you don't have quite that issue. I mean, whoever's watching, if you're not a bot, you can feel free to leave a comment. We can always chat. I'm always open for chatting if you got questions or if there's something you want me to cover. Chat doesn't want to talk. That's okay. I am willing to just keep going. So those are some of the structures we have inside of C. Let's look at NASM. I think they have the struct. Yeah, it looks like we can use either one of those. You have to use a struct and a struct end, so that is interesting. Yeah, let's we'll grab theirs. Let's see. This defines offsides. So sometimes you only have to address the structure displaced by an offset. In this case, you could access by subtracting the offset. So having defined a structure type, the next thing you typically want to do is declare instances of that structure in your data segment data. NASM provides an easy way to do this using the iStruct mechanism. To declare a structure of type myType in a program, you can do something like this. See, I'm wondering, so here you're just getting an offset, but here you can myType struct is not valid. Empty word is a constant. So the correct way is mystruct plus myword, or mystruct plus myType dot word. That looks interesting. So I wonder if, I don't think they'd have to be in the data segment. Yeah, we're not doing anything. So resd, that should be it sounds like that's in the BSS. Unless it's using just the same syntax. Which one should we use? I don't know. I mean, I had looked at it a little bit. Howdy. I got one person. Feel free to make suggestions or ask questions if you're in the chat. I try to look over. It's on another monitor, so sometimes it's hard to see. So I wonder. Is the array implementation part of the series? I'm guessing you're meaning. Yeah, we'll talk about arrays in this series. I haven't gotten there yet. I try to cover stuff on stream before I cover it in the series. That way we can I can work out all the kinks in it. So I'm thinking if this is, let's see. So we could say extern malloc to tell us that it's not here. And I think if we looked at our object dump, so malloc took a size. It should take a size. There's a second malloc call. Where was that? Oh, there's my other one. Okay. So it's using EDI or RDI. So EDI. So we can move RDI 100, call malloc. So that should be in RAX. So we could store it in a register, or we could save it in a pointer. So DQ, let's see, my pointer DQ, I'll give it 0. It's could be whatever. LEA. Let's do R8. The value of my pointer. So that should load that address into R8. Then we can move into the location at R8. RAX. Yeah, I figured. So I think I got to say this with respect to. Oh, is that going to work? Got Oh. God, I hate 64-bit kicking my butt. Oh, I think I gotta use oh, we did this. I did this a couple times ago. I always forget the new syntax. NASM. No, which program did I do that in? Did that in one of them. Let's look. Assembly isn't commented like that. Well, you know, try and add comments. This is my template, so my template has a bunch of comments in it, just so we know what we're doing. Oh, let's see. Grep minus. Oh, I always forget this command as well. Grep search directory recursively. That's what I wanted. Okay. ASM files. And I want to search for with respect. Okay. There we go. With respect to the so it isn't, so that looks like, yep, it's in my IO library. So let's look at my IO library because I did it there. You only use grep minus I. Yeah, I mean, you can also use find if you want, and then pass it through grep and do a print. I get spoiled with Visual Studio because I can do a full text search. That's not the one. Where is it? PLT. Maybe I just don't need my brackets. Maybe that's where I'm. No, that seems right. Oh, well, it's. Did I not put default rel? No, it's default rel. That's segment data. Yep. Well, that load stint should work. Oh, I think it was the. Oh, 32-bit is probably where my. So this should work. Maybe I'm just doing the wrong one. Oh, make. Oh, cd dash. Oh, I didn't even read my darn message. With respect to PLT. Ha. Yeah, you're talking about a grep. I recently did a project where I had loaded everything into a database. Did a bunch of work around that, and then found out that it's actually faster to just load the whole darn thing in RAM and search it from there in Python. It's like orders of magnitude faster than doing a bunch of database queries. So sometimes you learn doing stuff the hard way. Okay, so I was right. The more complicated way is when we have to do it in 32-bit, and then it all becomes more difficult because of the way 32-bit works. I was working on the 32-bit versions of the libraries and building a macro to do that. Oh, at least they had it, but you're moving into it the address of the global offset table, which is a symbol, and then subtracting out, and then using the local address of the program counter. It's a pain. Like, this looks terrible. Like, remembering how to type that is like my worst nightmare. Like, I just forget. I know I got to use the global offset, but you have to use a base address, which typically needs to be in a register, and so you got to call your get-got function to do a call for the next line, then pops it off, gives you the address, and then you can do a relative address from there into it. But 64-bit should be easy. Okay. So let's see if we can do this. So it is in RAX, so we should be able to access it. So if I wanted to move a number into MT long, let's see, MT byte, that'll be simple. So what is the manual saying? Not the manual. That is definitely not the manual. Okay. NASM structure. So I can say my type dot MT long. Oh, MT long is boring, but let's see, MT string. MT string. So I think I should be able to say, like, I'll just leave it. So RAX plus MT string. Is that right? Oh, yeah. So I'm always going to get that wrong. I want to move a byte. This is what I want to say. Yep. And we can, instead of dumping main, we can do ASM main. Yeah. So, yep, so it's just filling in that. So I guess it's just giving us raw access to that. So what does this other one do? So the reason the above code defines 6 symbols, MT0 is 0, so these are offsets. Okay. Oh, and my type is off itself as 0. Okay, I guess that's fine. The reason why the structure would be defined as 0 is a side effect of allowing structures to work with the local label mechanism. If your structure members tend to have the same names in more than one structure, you can define the structure above like this. So the dot means it's hidden, right? This defines the offsets to the structured field as my type dot long, my type dot word. I don't know, that seems better. Don't you guys think? If we do a dot, then they're hidden, and you'd have to do an add. So then it's my type. So Wolfram, what do you write assembly for? If you feel like sharing. Since your code doesn't look as clean as mine. Or comment it. It may be better. Who knows? So that does compute to 7. Yeah, I mean, I guess either one of these would be fine. I mean, the goal is to do this. I don't know which one's better. Wikipedia? Core War. They have a website. Is that one? Yeah. Like, I want to do this, but with like real code. Like, we don't need some fake assembly. I don't know. I think there's a lot of different things we could do with it. You know, you could make different ways of like 2 assembly programs, say in a gigabyte of space, and you only got 1 thread. Like different ways they could try and find each other or different methods of winning. So for example, if you can make one of them, say, return your ID, right? So you don't know their ID and they don't know your ID. But if you can make them exit and return your ID, then you win. So you don't get to just crash them. Like you got to write into their code somewhere this return that actually causes them to return your address. I don't know, that'd be one way, or making it like, what's that game? Brick Breaker. Like having a buffer where like you can go through different system calls and then be able to sort of destroy something. And if you destroyed all the blocks around it, then you're allowed to destroy it. Like it's got to be, say, free on one side before you can destroy it. And then when you've broken through that, then you can attack their code. Like that would also be fun. But I think we'll have to develop a game engine around it. Like I'd like to be able to visualize it, like to see where code is running, see where things are writing, see where things are reading into that. So, but I don't know. I probably should get back to work here, but if you guys have any questions or comments, feel free to leave them. You can always message me on Twitter. I'll put a link here. Grab my handle. That sounds interesting. A CPU path tracer. That does sound interesting. Yeah, I've been looking at doing some ML type things. Um, we got a bunch of machine learning stuff that we can do, and I didn't want to stream on it on this channel, but like I think it would be interesting to, as somebody who hasn't done actual machine learning, to be able to learn how to do it and use it in the stuff I do at work. I think would be fun. Um, so I think that sounds fun. Sounds like you got to do a lot of fun things there. I haven't looked at this Embry code. Anyway, yeah. So my Twitter handle is Millhouse30. I don't know why it won't chat won't let me do it. It's hating me right now. I think Restream has failed in some weird way. Yeah, I think I can send it here. There we go. Ah, yeah, my thing in there is broken. But anyway, well, we'll try and do a couple more this week. So if you guys are on, just feel free to reach out and ping me on Twitter, and we can always start up a Discord server if you guys are interested. So, but I'll let you go. Thanks, guys. We'll talk to you later. Bye.